welcome to these lectures on algebraic geometry and commutative algebra. In the last lecture I have proved Hilbert basis theorem, and that gives us lots of examples of Noetherian rings. Also we have been studying Artinian modules and Noetherian modules, and we have collected number of statements, but still I need what is called structure theorem for Artinian rings, and I will prove it soon. But before that I want to give one more very important application of Hilbert basis theorem. So for that let us recall definition of a free module. So recall that so definition, this you might have learnt in your first course on algebra. So let A be a ring and V be an A module. We say that V is a free A module if V has a basis, that is there exists a generating system Vi I in I of V which is linearly independent. Over A. So this means, so that is basis. What is a generating system? That means every element of V is a linear combination of these Vi's. So that means V equal to, in our notation, V equal to summation I in I AVI. This is the smallest submodule of V which contain all the Vi's is V, and linearly independent means if a linear combination, if summation Aj Vj J in J, where J is a finite subset, if such a linear combination is 0, then Aj equal to 0 for all J in J. And you have seen in your linear algebra course that every vector space has a basis. In fact, that was the first theorem in linear algebra 1 proves that every vector space has a basis. But unfortunately this theorem is not true for arbitrary commutative ring. Even for Z it is not true. So let me give first one or two examples. So let us see some examples. We have seen earlier that abelian groups are precisely Z modules. So in particular finite abelian groups are Z modules. So the first one, every finite abelian group G does not have basis, does not have Z basis. That is because in fact every element of G is linearly dependent over Z. Since if I take the order of this group G, that is cardinality G times any element of G, I have written the group abelian group, so I am writing them additively. So this time G is 0 for every G, and this cardinality is an element in the it's in fact a non-negative integer. So therefore even every element satisfies a dependence relation, so it cannot have a basis. So therefore finite abelian groups are not free Z modules. So in particular G is not a free Z module. Okay, another example we could give is, so in fact I is any set, any index set, and consider this notation A any ring, and we have this A power I. These are the A valued functions on the set I, and there we are taking this as a component wise addition. With that it becomes an abelian group, and also we are taking component wise scalar multiplication. So this is component wise addition in the ring A, just push it in. So that is, if I have a tuple AI and I have another tuple BI, then you define this to be AI plus BI, and then it's again an element in the tuple. So this becomes an abelian group. So abelian group with respect to the component wise addition, and scalar multiplication is A times the tuple, push that inside, or component wise scalar multiplication. So these I will keep referring component wise scalar multiplication. So with that this becomes a modulo over A, and but if I may be infinite set, so among that I consider this round bracket I, this is a subset of A power I. I do not take all functions, but you take the functions f from I to A such that f of I is 0 for almost all I in I. So if I were a finite, then it will be equality if I is a finite set. Otherwise it is not equal. So this one is clearly a submodulo of, so this A power I round bracket I is a submodulo of A power I, and we claim that this module is a free A module, and in fact you can classify free A modules like this. So let us prove that. So, A power round bracket I is a free A module with basis EI, where these EIs are the functions from I to A which maps I to 1 and any other j to 0 for j not equal to I. And now I will, it's almost clear, or you would have done such a checking in linear algebra course, the same checking, that EI, I in I, check that this is a generating system and linearly independent. So, it is a basis of A round bracket I over A. That means they are linearly independent over A. Alright, so but the big module A power I need not be free actually. So, I will just remark here, which is not so easy to prove. A power I need not be a free module, free A module. That means it may not have a basis in general. This needs proof. I will try to see when I can prove this, or at least add in exercises. Alright, now another remark is any free module is isomorphic to this. So, conversely, if V is a free A module with basis Vi, I in I, then the map from A power I round bracket I to V defined by EI goes to Vi. So, this means if I take any element here, the any element will look like AI EI with almost all AIs are 0. This maps to summation AI Vi. This makes sense because this is almost all AIs are 0. So, it is a really finite sum, finite sum. So, this map defined by this is an isomorphism of A modules. So, we will have to check that this map is injective and this map is surjective. So, injectivity corresponds to the fact that these elements are linearly independent, and surjectivity corresponds to the fact that it is a generating system. So, the same thing one proves in linear algebra, and so I will not going to give details of this. The language is same. In fact, for more on linear algebra, you could also see my linear algebra course in 2017. So, their notation etc. will be the same. So, you will not have much problem with that. Now, the question is, like in linear algebra, you prove that any two bases have the same cardinality, and now one may wonder whether the same theorem is true. Well, yes, it is true, but the ring commutativity of the ring is very, very important. If you drop the assumption that the ring is not commutative, these concepts, free modules etc., you can define for arbitrary ring, but then the rank when one say rank, that is the number of elements in a basis, and these should not be dependent on the basis. This theorem will not be true anymore. But since I am not going to do non-commutative rings, I will not worry about non-commutative rings, but for commutative rings I will prove this. So, now let me write a commutative ring. And the theorem I want to prove, let V be a free A module and Vi I in I, V prime J, J in J, be two bases of V over A, then cardinality of A equal to cardinality of J, and this cardinality is called the rank of A, rank of V as A module, denoted by rank A V. So this notation is a little bit different from the basis, because we have to distinguish. So in particular, when A is the field, then this rank is the dimension. So for A equal to K field, we denote rank K over V is also denoted by the dimension Kv, is called the dimension of V over A over K. Well, this theorem also we will prove that in particular, because we are not assuming anything on the ring, and the way I will prove this theorem, I will not use a linear algebra theorem. Of course, one way is to reduce to the field case and prove this theorem, but I am going to prove in a different way. But one step I will put it as an exercise, which is very simple to prove, that will be written in the exercises, and I will use Hilbert basis theorem or theory of Noetherian modules to conclude this. All right. So we want to prove this. Okay. So if you remember how it was proved for linear algebra, so let me start writing the proof. Okay, and one very important thing I must very important thing I forgot here to mention, A is non-zero ring. This is very important. Well, fields by definitions are non-zero, so I can apply it to the field case. All right. So let us start writing the proof. Okay, proof. So it is enough it is enough to prove that such a step also we have done in a linear algebra proof also. It is enough to prove that if so I am going to prove this statement only for we will prove only in the case when V has a finite basis. Because even in the linear algebra case, we have divided into two cases, V has a finite basis and V has infinite basis. And as you saw, infinite basis case was very easy provided you are allowed to use Zorn's lemma, and the same proof I would say. So, we will concentrate on the finite basis, and in linear algebra case we have proved something called exchange theorem, Steinitz exchange theorem, which you replace one basis element from the other and keep doing it. So, if you note that statement, it was enough to prove that if V has a generating system with n elements, then every n plus 1 elements in V are linearly dependent over A. If you prove this statement, then we would have proved that in the case when V has a finite basis, then the other basis is also finite, and this will tell one cardinality of one basis will be less than cardinality of the other basis, and now interchange the roles of the basis, then you will get equality. So, the crux of the matter is what I underline. If V has a generating system with n elements, then every n plus 1 elements are linearly dependent over Z, and V is actually an arbitrary module. And if you prove this statement, then as a consequence we will conclude that if V is a free module with a finite basis, then every other basis is finite and they have the same cardinalities. So, let us prove this statement. So, proof of this. So, how do we prove? How do you come back to Noetherianness? That is very interesting. So, V has a generating system with n elements means, so we have given that V is generated by n elements. So, let me write those elements as this x1 to xn, that is the generating system of V as a module consisting of n elements. And suppose y1 to yn plus 1 are arbitrary elements in V, and I want to prove that they are linearly dependent. So, suppose the contrary. Suppose on the contrary that y1 to yn plus 1 are linearly independent over A, then we should get a contradiction. Okay, contradiction to what? Okay, so very simple. From this, so I am not going to prove this, therefore I will write in a different color. So, then from these n plus 1 elements which are linearly independent over A, then construct a linearly independent countable family, countable infinite Z nu, nu in n, family in V and linearly independent over A. From these n plus 1 elements you construct more and more and more and more elements which are also linearly independent in V. Of course, you will have to use the fact that V is generated by n elements. Using these two facts you generate or construct countably many infinite linearly independent elements in V. And now we are done. So, after this let or put W be the submodule of V generated by these countably infinite families Z nu, nu in n. This is a submodule of V. This is the smallest submodule of V which contain all these Z nus. So, this is submodule generated by these linearly independent elements Z nu, which are linearly independent. So, therefore, note this W is generated by a linearly independent family, therefore, by definition W is a free A module. Therefore, W is a free A module with basis Z nu. In particular, this W cannot be finitely generated, because if it is finitely generated then it will involve only finitely many Z nus, and therefore, if I take any element Z nu which is which does not appear in any generating element, then that will be, because it is linearly independent from the other elements, that will be a contradiction. So, in particular W is not finitely generated A module, since every generating set of W, every finite generating, if at all, every finite generating set of W contains only, it is confusing. So, I will just say that every finite set, every finite subset of W contains only finitely many Z nus, nu in I, where I is a finite subset of n. This is finite, and if I take any nu which is not in I, Z mu cannot belong therefore to the submodule generated by this finite set A Z nu, nu in I for every mu in n which is not in I. This is clear because if this belongs here, that means you will have a linear dependence relation among z news, which is not true. So, no finite subset of W can generate W, therefore, W is not finitely generated, but on the other hand W is a submodule of V. This is a submodule, and this W is finitely generated. So, that's okay. So, from here conclude that this is not possible. Because see, you can also reduce this data to a finite. So, like in earlier statements, how we have reduced to the ring A is Noetherian, because only finitely many equations were involved and we put the coefficients there and took the Z sub algebra generated by those. So, use similar techniques to assume, we may assume that the ring A is Noetherian. And then because this W is finite, V is finitely generated, therefore V is also Noetherian. A module, but then W has to be finitely generated. Submodule of a Noetherian is finitely generated, so that will contradict. So this is not possible. That this W Noetherian should imply W is also finitely generated. A contradiction. This is not possible because we have noted W is not finitely generated. All right. So, how did you conclude? Because we have assumed the ring is Noetherian. So, if at all you want to, if things are not clear, you start with a Noetherian ring and then reduce to Noetherian case because finitely many equations. So, we have two things in this proof very important: how to reduce to the Noetherian case and how to get from linearly independent elements many linearly independent elements. Both this part I would write in exercises with elaborated hints so that it becomes a merely checking. So, with this I would stop this half of the lecture and I will continue this by studying little more properties of the Noetherian and Artinian modules, which anyway we will need it in the later part of the course. So, thank you.